Yeah, I think we should go ahead and get started. And I'm actually going to pass it to, well, actually, I'll do very quickly. I'm Kara Colton. I am the Director of Nuclear Policy at the Energy Communities Alliance. And I am thrilled to be handing it over today to Sarah Templeton, my colleague, who will lead us for the call.
Hi, everybody. For those of you that I have not yet had the chance to meet, my name is Sarah Templeton, and I am the program manager with the ECA. And I wanted to give a brief overview of the agenda for today. We will be starting with a few words from Mayor Rebecca Casper of Idaho Falls, who serves as the ECA New Nuclear Subcommittee Chair. She will be handing it over to Judy Greenwald, who is the Executive Director of the NIA. Next, we will hear from Dr. Patrick White on the NIA's Advanced Nuclear Reactor Technology Primer, and then we will kick it back over to me for a Q&A session. So with that, I will hand it over to Mayor Casper.
Very good. Thank you, Sarah. Good morning, everybody. As mentioned, I serve as the mayor of Idaho Falls, and also very excited about ECA's new nuclear subcommittee and the work that we're doing and trying to help us as members of this organization to better understand the players, the challenges, and the opportunities that are all related to the development of new nuclear missions all across the country. This is the latest in a series of webinars. So we're excited today to meet and hear from folks from the Nuclear Innovation Alliance. This is, for those of you who aren't familiar with NIA, it is a think and do tank. And I like that a lot because it connotes something more than just sitting around thinking, right? There's action. And so they are looking at how to enable nuclear power as a solution to mitigate climate change. Last month, NIA released an excellent educational tool, as has been mentioned. This is a primer entitled Advanced Nuclear Reactor Technology, a primer. And sorry, my notes just disappeared from my screen. There we go. Anyway, in order to go from the think to the do, I think I know I have to understand the why. And I think this primer very much helps us to get to that point. Sarah shared that with all of us last month, and I'm hoping that many of you have had the chance to click and to review it. It's 44 pages long. You may not have been able to sit still long enough to read that on your computer screen, but even just scrolling through, you can start to see how the information, the photos, the diagrams are all sort of there to help us to understand. So today, Judy and Patrick are going to walk us through that report and help us discuss how we can use it to help each other moving forward and use it to leverage support for the things that we're maybe trying to do in our communities. So as Sarah mentioned, a very simple report or a very simple format with our two speakers and then some discussion with our group. So first up is Judy Greenwald, and I'd like to introduce her. She serves as NIA's Executive Director. She has a lot of energy and environmental policy leadership experience, about 35 years worth, I'm told. And she has worked in the public and private sectors, including work with Congress, the White House, EPA, Department of Energy, the NRC itself, and the Center for Climate and Energy Solutions. Formerly, it was the Pew Center on Global Climate Change. Those are all incredibly impressive credentials. And so, we have to look forward. I'm looking forward to this. Judy has extensive experience focused on deep decarbonization, which is a relatively new term that's been out for a couple of years now. And what I have here is that extensive experience focused on deep decarbonization through the interplay of public policy, technical innovation, human behavior, big factor there, and then markets, another gigantic factor. And so she's going to tell us a little bit more about NIA's mission and what they're hoping that this primer will be able to do for us and for this larger cause. Then we're going to hear from Dr. Patrick White. He's one of the newer members of NIA's team. He's a newly minted graduate of MIT, and I'm told he has the rare gift of being able to transform technical terminology into relevant insight. And he's going to perform that magic for us today. In order to go from that think to do, we have to understand the why. And so when Judy and Patrick are finished, Sarah will then take over and guide us through the Q&A. So let's get started. And Executive Director Greenwald, it's all yours.
Thank you so much. Welcome, everyone. Thank you to ECA for inviting us. And thank you, Mayor Casper, for your very generous opening remarks. And really excited that you're chair of the new nuclear subcommittee. And that's a near topic that's, of course, near and dear to our hearts. We're excited to be here today to tell you about our new primer, as well as to talk about a little bit about NIA, which is where we'll start. We also hope to spark some ideas among you all on how our two organizations might work together to realize our shared goal, which is to support the research, development, demonstration, and deployment of advanced nuclear reactors as part of a carbon-free, resilient energy system. I guess we can go to the next slide. NIA, as Mayor Casper said, is a nonprofit, nonpartisan think and do tank. I'm glad you like that term, working to create the conditions for success for advanced nuclear energy as a climate solution. Through research, analysis, and education, we inform decarbonization and innovation policy. And we also collaborate with stakeholders to coordinate advanced reactor advocacy in the United States. We're funded primarily through climate philanthropy. And I, of course, come at this issue from a climate and energy systems perspective. Our board of directors and advisory committee both include academics, industry leaders, finance and investment professionals, key stakeholders, and nuclear thought leaders. And we also receive input from our Industry Innovation Leadership Council, which consists of experts and executives from the leading advanced nuclear reactor developers in North America. Next slide. NIA has focused since its inception in 2015 on creating the policy environment needed to support advanced reactor development and deployment. We played a leading role among informing major federal legislation to reform advanced reactor licensing at the Nuclear Regulatory Commission and to expand the Department of Energy's nuclear innovation efforts. NIA aims to impact ongoing conversations on issues critical to the successful deployment of advanced reactors. Please check out our website if you're interested in the variety of technical and policy publications that we've produced. For example, in February, we released U.S. Advanced Nuclear Energy Strategy in collaboration with the Partnership for Global Security. And this report laid out a joint strategy for U.S. leadership on commercialization of advanced reactors, a whole of society approach with collaboration between government, industry, civil society, and other nations in order to bring advanced reactors to market to reduce global emissions, provide domestic jobs, and support national security. Next slide. Now today, we're happy to discuss one of our latest publications, Advanced Nuclear Reactor Technology, a primer. And we created this primer as a guide for media, congressional and administration staff, elected officials, folks like yourselves and others to understand the rapidly evolving advanced nuclear energy space. It's intended as a 101 document to demystify advanced nuclear reactors and explain the characteristics of the most common types and leading designs. For some context, the commercial nuclear industry in the United States has over 60 years of experience in designing, constructing, and operating light water nuclear reactors. The conventional technology that's in use across the country is well understood by a host of players, scientists and engineers, of course, but also policymakers, journalists, academics, and other stakeholders. However, due to a host of emerging factors, especially growing concern about climate change, shifting energy market demands, improved computing and engineering competencies, and heightened interest from financial investors, new advanced nuclear reactor designs are now increasingly viable, both technically and economically, with some in various stages of R&D and others being demonstrated within this decade. Yet with the exception of a handful of hardworking policy wonks in DC and a collection of engineers across the country, there are very few who can easily navigate this new technical landscape. In ECA's case, it's our intention that this primer can provide what you need to know to engage in conversations and negotiations with advanced reactor developers to not only understand reactor design features, but also what the benefits of those features are for the environment, for economic development, and for your communities. This primer is part of our effort to be an even greater resource for you, your staff, and other key stakeholders and policymakers. If you ever have questions or know of people who do, we hope you'll consider us as an information source along with your great staff at ECA. As we release additional publications in the coming weeks and months, we do hope you'll engage with them and with us. And we also invite you to tell us what additional information and resources would be helpful to you as we plan our future work. So thank you again for allowing us to present to you today. I'll now turn things over to Dr. Patrick White, our project manager at NIA, for an in-depth review of the primer. Thanks.
Great. Thanks so much, Judy. Yeah, very excited to be here talking about the primer. I'm a huge fan of nuclear energy and I love sharing it with people. So I hope to answer a lot of questions and cover some of the really interesting high points of the presentation today. So as we jump into the primer, one of the things that's really important to know, if I can go to the next slide, is that most perceptions of nuclear energy are really based on the conventional nuclear energy. And I know for me growing up, it was what I saw on TV. And so of course it was The Simpsons, the Springfield nuclear power plant. You might laugh at this picture, but if you take a closer look, you see it actually looks pretty similar to real nuclear power plants. So in this case, it's almost a one-to-one match for the Byron generating station in Northern Illinois. And so when we think about nuclear energy, we might think about, okay, what does this plant look like and what does this plant do? And so there are a lot of different ways that we can think about the characteristics of different nuclear power plants that help us understand what they are, and then also might help us understand what the differences are between kind of conventional nuclear, the existing nuclear power plants that we have today, and advanced nuclear power plants, the power plants that we're hoping to build in the future. And there are a couple different buckets that we can throw this information in. There are three that relate closely to design, which are the reactor coolant, the reactor fuel, and the reactor power level. And then maybe four characteristics that describe how the reactor operates. In this case, what its use cases are, what its construction logistics are, what's really the approach to reactor safety, and what are some of the kind of community requirements, or how does it really interact with the community? And so what we can do is we can start to characterize each one of these different attributes and start to get a better understanding of advanced nuclear technology and what some of the potential advantages might be. And so just to kind of quickly bring everyone up to the same level, when we talk about reactor fuel, we're actually going to talk about what is the form of uranium or other nuclear material that's inside of the reactor that's being used to generate the heat that's ultimately powering the turbines or our other energy generating systems. So that's going to be the reactor fuel. The reactor coolant is going to be whatever material is used to take that heat from the fuel and then take it either to our industrial facilities or to our turbines or our generators or anything that's actually making the electricity. How is that heat energy actually moving? And then the final one is just going to be the reactor power level. How much power is actually being generated by this reactor? Is it enough to power 100 homes or 1 million homes? And what we can do is if we start looking at kind of each one of these characteristics of the coolant, the fuel, and the power level, we can start to get different insights into how these advanced reactors might operate and how they're going to differ from conventional plants. So if we take a look at this conventional reactor, we can start to say that it has a light water, so it uses just normal water as its coolant. Its fuel form is going to be ceramic low enriched uranium, or LEU. It's actually about a little pellet about the size of a pencil eraser. And it's a very large reactor. It has a power rating of over 1,000 megawatts electric. And so that means it's going to power almost over 1 million homes just with a single reactor. And so if we take a look at kind of these three characteristics, it leads to having some interesting plant attributes. Really, it's designed and operated now to make base load electricity. It produces the same amount of electricity, full power, 100% of the time. A lot of these are custom plants or maybe plants that have one or two related units, and we're really just kind of built on site. So each one of these plants is kind of a unique thing. It relies on active safety systems, rely on pumps that need electricity, valves, other systems to help keep the plant in a safe state. And we are able to keep it in a safe state, but it definitely takes more engineering than other reactor technologies might. And when we look at kind of community requirements, we really rely on kind of siting away from population centers. You don't normally see a nuclear power plant built right in the middle of a large city. They tend to site them outside as a way to kind of provide a little bit of additional safety. And so when we think about this, this is kind of the typical conventional reactor, and it met a lot of the engineering and utility needs of the past. But what we've seen, especially in the last few decades, is that the way we're thinking about energy and the way we're thinking about electricity is rapidly changing. The idea of kind of the large utility making these reactors that power 1 million homes is starting to become maybe not aligned with the clean energy future that we're thinking of. And so what we have are now definitions of what advanced reactors are. How might an advanced reactor differ from the technology that we're currently using? And so advanced reactors have been very broadly defined by regulators to kind of meet future energy needs. So in this case, I'm going to go ahead and give just the set definitions that come from the United States Nuclear Regulatory Commission on what are the potential advantages of advanced reactors. And these are kind of the weird definitions that they use. They don't say what technology an advanced reactor might be. Instead, they say what might an advanced reactor do? And that's the way the definitions are set. So some potential advantages of advanced reactors include inherent additional safety features. This is the idea that it's a safety feature that doesn't necessarily rely on a pump running or a valve opening. It just is a safer technology that doesn't require some sort of intervention. An advanced reactor might have a significantly lower levelized cost of electricity. That would be a great thing for an advanced reactor to have. It might have a lower waste yield. So it might produce less spent fuel or less amounts of other radiological wastes. It might have greater fuel utilization. So the uranium fuel that we put inside of a conventional reactor, we only actually use a small percentage of the available fuel inside of that fuel pellet before we have to stop and essentially put it off as spent fuel due to a lot of reasons related to the design of the reactor and the way the reactor operates. So there's some talk, what if we could try to get more energy out of every single one of those pellets with an advanced reactor technology? So that'd be an example of greater fuel utilization. Greater enhanced reliability would be a really interesting really interesting attribute for advanced reactors. Increased proliferation resistance. This is an interesting one because it starts to get into the discussions of not just nuclear energy in the United States, but export of nuclear energy abroad. How can we allow other countries that might not necessarily have the same safeguards and controls the ability to use advanced reactor technology with fewer concerns about the potential proliferation of nuclear material? And so that's the idea of, could we design reactors that are intentionally designed for that? Increased thermal efficiency. This is just a reactor that more efficiently uses the resources that we have. And finally, the ability to integrate into electric and non-electric applications. Like we looked at with the conventional reactor, a conventional nuclear plant is one that just produces large amounts of electricity for the grid. But there are a lot of really interesting opportunities to use nuclear energy to help decarbonize or provide clean energy for other sectors. So instead of having to burn natural gas or oil to support some industrial activities, what if you could use a nuclear power plant to provide that type of heat? And so that's one of the potential applications of an advanced reactor. And so if a plant could do that, it would qualify under this. And so this ends up being kind of a very broad list of different attributes a reactor might have, and that could be attractive for a future technology. And when we take a step back, we can start to think about how the design choices, this reactor coolant, the reactor fuel, and the reactor power output, are going to relate to kind of these different advanced reactor advantages that we just talked about. And then finally, they feed into this idea of how are we using the reactor, how could it be constructed, what's safety, and what are some of the requirements on the community. And so what we're going to do is spend a lot of this presentation kind of walking through this coolant, fuel, and power output to start giving all of you some interesting insights on how, when a reactor technology developer describes their reactor as a salt-cooled reactor, what does that actually mean? And how does that tie to the things that we ultimately care about, whether it's a safer reactor, a more affordable reactor, or maybe something that has new use cases that we haven't thought about. So as a quick example, if we took a look at the power output to the way it relates to reactor use, we can start to kind of really understand how these design choices relate to the advantages. So let's say we had a microreactor. It's a very small nuclear reactor, less than 30 megawatts electric. So if you can think about that, it's a fraction of that 1,000 megawatt reactor that we currently use. Well, if we went down that list of kind of advanced reactor attributes, we could see that a microreactor would have the ability to integrate very interestingly into electric and non-electric applications. Maybe it's not trying to power an entire city, maybe it's just trying to power a small community. We can then relate that to a use case of maybe we could use microreactors to have remote or off-grid applications. Instead of relying on diesel generators for a remote area or having to bring in natural gas or other fuel, what if we had a small nuclear reactor instead? It meets the size of the application. And so this is just one of the ways you can start to think about the technology of the reactor and how it ultimately relates to the things that we're interested in. How can it have a bigger impact on our communities? And so what we're going to do, and what I think the primer does a pretty good job of, is starting to walk through each one of these different steps and say, so what? You've got a microreactor. What does that tell us? And so we'll go ahead and walk through coolant, fuel, and power output. So the first one that we'll start with are reactor coolants. And so reactor coolants are really interesting because when someone's telling you about a brand new technology that they're working of or that they're interested in, you start to get the insights that's going to really affect the reactor temperature, the reactor size, and the reactor safety. So if we take a look at kind of a conventional nuclear power plant, like I said earlier, a lot of them, or at least all of them in the United States, use light water, just honestly normal water right out of your bottle, but highly purified. And so you might say, okay, what does that actually mean? How does that affect some of these bigger things that we care about? Well, with light water, it's a really well understood technology. We have a lot of experience in operating systems that use water. I mean, even back to steam engines, and we really understand the properties. So we really understand how to use light water as a coolant. The problems are it has a few potential drawbacks you have to engineer for. Things like a lower boiling point or a higher pressure. And so this means that you have to have larger systems to control it. It might have a low energy storage capacity. One of the challenges associated with this is that if you start to have an incident where you need to kind of turn off your reactor quickly, it might be possible for the reactor coolant to boil off, and you might lose the material that you need to cool your reactor. And that could be a downside. And finally, it has this property of being reactive under some conditions. And I'm sorry, are you guys getting a little bit of feedback, or is it not coming through? Great, my microphone is a lot better than I thought. There's a buzzsaw going on in the background, and I just want to make sure it wasn't coming through. And then the final issue is that it can be reactive under some conditions. And so this actually relates really directly to the Fukushima nuclear accident. A lot of you might have heard that there was some hydrogen that was released during the accident. And that was actually due to a reaction between the light water coolant and the metal that surrounds the fuel inside of the reactor. Under very high temperatures, the water can release hydrogen gas, and that can become a significant safety issue. So while water has a lot of advantages, there are potential issues with it. And so what we've looked at when we look at advanced reactors is how can we use different types of coolant, such as molten salts, gas, liquid metal, or heat pipes, to try to overcome some of these and have potential new advantages. And so let's go ahead and jump into some of these. The first one that we could talk about would be molten salts. And so these are molten ionic salts. They come under a couple of different names, things like FLiBe or FLiNac. And the way to read these are actually the combination of chemical elements that are used in it. So when you look at FLiBe, it's big F for fluorine, Li for lithium, and Be for beryllium. So FLiBe is going to be a fluoride lithium beryllium salt. When you hear something like FLiNac and someone throws around that term, it's going to be fluoride, lithium, sodium, and potassium, because potassium starts with a K because the periodic table is a strange thing in that way. And so molten salts are a very interesting potential coolant for advanced reactors. Unlike some of the advantages are they have a really high boiling point and a really low pressure. So unlike a water-cooled reactor where you need to have really thick pressure vessels to try to hold back this very high pressure, with a molten salt reactor, you can usually have thinner walls, or if you do have a break in the pipe, you're not worried about the water spraying out under extremely high pressure. In this case, the molten salt can just be operated at lower pressure, and you don't have to worry about it boiling, which is a really nice advantage. It can really store a lot of heat and has really good heat transfer, which allows for a very compact reactor design. And so it's, again, a significant potential advantage of using molten salt as a coolant. Finally, it has this property of retaining radionuclides. So if during the operation of your reactor, some amount of radiation was released from your fuel, the molten salt has a very good property of actually binding with some of those chemical elements and preventing them from being released further out into the environment or out into other plant systems. And so this is a potential advantage of looking at molten salts as a coolant. That being said, it does have some engineering challenges. Things like it has limited experience actually operating these large systems, and some of the systems are going to be a little bit harder to engineer and maintain. We just haven't built a lot of reactors with molten salt before. So any companies that are really interested in developing this technology are having to figure out how can we start to develop experience with it so we can design really efficient systems. And so if you look at some of the advanced reactor developers, you can actually see that their demonstration and test plans start looking at how to build non-nuclear prototypes first, get experience with the salt, and then apply it to the larger nuclear reactor system. That's the way they're kind of overcoming these challenges. And so if we look at the potential advantages, we can end up with an inherently safer reactor with potentially lower electricity costs just due to the savings on the plant size, an increased thermal efficiency because it's operating at a high temperature, and it could also integrate potentially into electric and non-electric applications. So you can see just by recognizing kind of what the reactor coolant is, learning a little bit about the coolant, we can start to tie it to these things that we really care about in terms of what is its performance as a new technology. So if we move to the next coolant, to gas, when we start thinking about gases, most often helium gas, it's a very, very well characterized coolant, and it's very stable to operate. So with gas, unlike water and even unlike molten salts, you don't have to worry about your coolant boiling. It's already a gas. So that means your reactor is always going to be operating under the conditions that it's designed for. It's very well characterized. We understand, we have a lot of experience in actually building and designing gas systems. Helium is a noble gas, so it doesn't have any reactions that we really need to worry about, and the systems are very easy to engineer. So if you choose helium gas as the coolant for your reactor, it means it's going to be a fairly straightforward characterization and stably operated reactor. A couple of the challenges you need to work through, however, is that it has limited heat transfer and kind of a low energy storage capacity, which means that you need to design your reactor to be a little bit larger to account for the fact that it's not able to remove the energy as efficiently as water or as a molten salt. And that you need to make sure you have other auxiliary systems to help remove heat after the plant shuts down. And so you can design for this, but it's not as simple as just, oh, let the water sit in the tank and absorb the thermal energy. So when we think about kind of, again, these advanced reactor advantages, it's also going to be inherently safe. It's going to have hopefully a lower cost of electricity because you're able to operate at higher temperatures. The enhanced reliability because you don't have any interactions between the coolant and any other things in your system. And again, kind of increased thermal efficiency and the ability to integrate into other applications, just because it is going to be a reactor that operates at a high temperature and that can hopefully kind of produce the conditions that you need to meet other decarbonization goals. The next coolant that we can jump to is liquid metal coolants. And this is a bit of an interesting one. Instead of having a salt or water, we actually take sodium and heat it up to several hundred degrees C where it melts. And then we're using this liquid metal to move through the reactor and move the heat. It might seem a little counterintuitive that something at 300 or 400 degrees is going to be the coolant. But when you're looking at a reactor fuel that's up above 700 or 800 degrees, you're able to kind of very efficiently move that heat with that liquid metal. And so when we think about liquid metal as a coolant, again, very high boiling point, very low pressure. This makes it so it's a system that's fairly easy, that's easier to engineer. It has very, very good heat transfer. I mean, I think anyone that knows having a metal pan on the stove, you're able to move heat through that material very, very quickly. It means that it's able to remove heat from the reactor very quickly. And it leads to a nice, compact, and a very small nuclear reactor. And we actually already have some experience designing and operating liquid metal cooled systems. For anyone that's out in Idaho, EBR2, the experimental breeder reactor 2, was a sodium cooled reactor. And so this is something that we've actually operated in real life. And now the question is, how can we take it from that experimental stage to a commercial stage? Some of the things you have to work with on liquid metal reactors are the idea that the coolant can be reactive. The coolant can react with air or water, so you need to make sure that you're designing your systems to kind of prevent those interactions. Sometimes actually using inert gases like helium or argon can be a really good way to prevent any types of those interactions. And sodium systems can be a little bit harder to engineer and maintain just because liquid metal is a little bit harder to handle than water. And so if we use liquid metal in our reactor, what are some of the potential advantages? Why are people interested in this? Well, it provides a lot of advantages such as kind of inherent safety. It can absorb a lot of thermal energy, significantly lower electricity costs, lower waste yields, and greater fuel utilization are a really interesting property of advanced reactors that use liquid metal because they are able to more efficiently use more of the fuel mass and hopefully get to what we call a higher burnup, or just using more of that uranium per unit of fuel. And that depends a little bit more on kind of the detailed reactor design. But the idea is a liquid metal fueled reactor could be a more efficient kind of burning nuclear reactor. The other advantages, again, that are common, you've probably seen this, the other fuel types, are increased thermal efficiency and the ability to integrate into electric and non-electric applications. I feel a little bit like a broken record saying this for all of these, but this is something that a lot of the developers are really looking at, is the energy grid of the future is really going to need to have this better integration in with all types of low carbon or clean energy systems. And so this type of integration is going to be key. The final coolant I'll talk about quickly are heat pipes. And so this is something that people might not be super familiar with, and it might seem a little strange. But what a heat pipe is actually a long sealed metal pipe that actually has a small amount of sodium move through it. And so the sodium will essentially remove heat at one end of the pipe and then transfer it without any kind of moving parts to a cool end. And so it almost becomes kind of a closed system where one end is hot and one end is cold, and the thermal energy is just transferred passively. I've got a slide on this later that we can talk about it if people want to get into heat pipes in a bit more detail, but it's a bit of a weird component where it's one end hot, one end cold. And that's kind of the very simple way it works. It's a very simple piece of equipment. But the advantage of this is that with heat pipes, you can start using higher operating temperatures with no moving coolants. You can use heat pipes to remove a lot of energy, and there are no corrosion concerns because it's a solid material. Oh, there we go. The downsides are it is less efficient, and we do have limited operating experience with these. And so the advantages of heat pipes is that it's really inherently safe with increased reliability, proliferation concerns, again, thermal efficiency, integrated electricity. The one thing is that it might not be lower cost, and that's kind of the one challenge, is that you need to have a lot of these small heat pipes, and it can only remove a certain amount of heat. So you wouldn't necessarily want to have a heat pipe reactor for a very, very large reactor, but it's well suited for smaller reactors. And so kind of with that, and just with that quick summary, you can kind of see that the advanced reactor developers have a whole menu of different coolants they can choose based on their desired attributes and what they're interested in. The next part I'll jump into is reactor fuel. And so this one I'll touch in a little bit less detail, but when we start thinking about reactor fuel, what's actually holding the nuclear material in the center of the reactor? It's really going to affect the temperature the reactor can operate, the economics, and the safety. So in the conventional nuclear reactor, we use the ceramic low-enriched uranium. And again, it's a very well characterized fuel form. We understand it very well. It's very stable and it's very easy to manufacture. It's a fairly good fuel. The problems with these is that they tend to have poor heat transfer and they can melt under certain conditions. And it requires a special layer of what's called metallic cladding or a metal tube around the fuel to prevent interactions between the coolant and the fuel itself. And that can lead to some of the challenges like I alluded to earlier at the Fukushima, during the Fukushima nuclear accident, when the interactions between the metallic cladding, the zirconium on the outside of the reactor interacted with the water coolant. And so to try to overcome these, we come up with a whole bunch of new types of advanced nuclear fuel forms that might try to get around some of these and bring new advantages. These include metallic fuels, what are called triso fuels, we'll get into that, molten salt fuels, where you actually have a molten fuel, and carbide fuels. For sake of time and for kind of what's under major development now, I'm just going to touch briefly on the metallic fuels and the triso fuels. But happy to take questions about the salt fuel and carbide fuels later if you're interested. So one thing I want to touch on quickly, again, just because it's kind of an interesting topic, is beyond just the form of the fuel, what it actually physically is, we can also characterize them by the amount of uranium-235 that's in the fuel. Now, for anyone it's been a few years since the chemistry course, uranium has a bunch of different isotopes, or uranium with different amounts of neutrons in the nucleus that affect the different properties. So the main isotope that we have of uranium is uranium-238. It's the most common isotope found in nature, and it makes up about a little over 99% of all uranium found in nature. And uranium-235, which is an isotope with 3 less neutrons, exists with about less than 1% in nature. The problem is the uranium-235 is what's called a fissile isotope, and that's the isotope that we're really interested in for producing power. And so what we have to do is we have to take this naturally occurring uranium and through a process called enrichment, change that ratio of uranium-235 to uranium-238. And we can almost kind of think of pure uranium-235 as being all the way on the right side of this, where we've gotten rid of all the 238 and it's just 235. So what we'll commonly do is we've defined a benchmark here of 20% 235, 80% 238. And we'll call anything below that 20% mark low enriched uranium, LEU, because we've only enriched it a small amount in that 235 isotope. And anything above that we call highly enriched uranium. And you can see kind of in between here, our conventional reactor fuels that's at anywhere between 4 to 5% uranium-235, while the research reactor fuels that were initially used in the United States is up near 90%. And we might say modern research reactor fuels are right about 20%. So you can see it's a whole spectrum of different fuels that you could use depending on the uranium-235 content. What we end up finding, however, is that due to the design of some of these reactors and the new coolants and new fuel forms that we're using, there's actually a need for this, what's called high assay low enriched uranium. So it's uranium that sits right in between this 5% mark and the 20% mark of uranium-235. And this has just enough additional uranium-235 atoms to allow some of these reactor designs to operate, but doesn't go into the range of kind of highly enriched uranium that we might be concerned concerned about for proliferation concerns. So quickly jumping into the fuel forms, metallic fuels are, again, are a very interesting fuel that allow for more efficient design and operation. They can operate often for longer periods of time, and we have a lot of experience and engineering experience with metallic fuels. Again, EBR2 is a really good example of we've actually operated fuels with metallic reactors, or operated reactors with metallic fuels before. Some of the challenges are that we've never operated these fuels for very long periods of time. So there's a need for increased testing and some fuel qualification to make sure we understand what this fuel would be like if we left it inside of a reactor for years at a time. For anyone that's interested in VTR, the versatile test reactor that's being proposed out at INL, VTR would be a fast reactor, a fast spectrum reactor, which would allow for the unique testing capabilities for some of these fuels. And so this is one of the reasons that some of the companies may be interested in that. When we talk about some of the potential advantages of the metallic fuels, really it's, again, just allowing for a more efficient utilization of the fuel with lower electricity costs and increased thermal efficiency. When we talk about TRISO fuels, that's a kind of a very different type of fuel that has very high stability. And so what a TRISO fuel is, it stands for tri-structural isotropic fuel form. And you can almost think of it as a tiny little poppy seed of uranium that's surrounded by layer after layer of carbon material. And that carbon material actually creates a bit of a protective shell around the uranium that helps provide a lot of stability and helps retain any kind of radionuclides. So it ends up being a very helpful, very useful, stable fuel form. The challenge of using TRISO fuels can be a little bit more challenging to produce those tiny little pellet or those tiny little poppy seeds. So with these fuel, you're basically trading some of the waste utilization and cost concerns for cost advantages you had with metallic fuels. But instead, you're ending up with a fuel that's very safe, very reliable, very proliferation resistant, and has a very high thermal efficiency. So you can see it's something where developers are really kind of making their fuel choices based on the desired attributes and the coolant compatibility. The last thing I'll just touch on very quickly is kind of really how reactor power size affects construction and safety. So we talk about conventional nuclear. It has economies of scale with very large reactors. It can meet baseload needs and aligns with capital, but it can be integrated to kind of integrate these very large reactors that we currently see into these evolving power markets, and that the high capital costs, the idea of paying upwards of $5 to $10 billion for a single reactor, might make it difficult to construct. So what we look at with advanced nuclear is how do we have smaller nuclear units that might fit into different niches in the new electricity markets. So when we think about large reactors, and these are reactors between about 300 megawatts and 1,000 megawatts, we might still have economies of scale from being fairly large, and we can meet larger energy electricity demands. The problem is it might require a little more energy storage to get flexibility with units that are this large, and they might still have significant upfront capital costs. It's still a fairly large reactor that you're building. And so you can have lower electricity costs and still integrate in with electric and non-electric applications. SMRs are kind of the next level down in size. That instead of that, they're really closer between 30 megawatts electric and 300 megawatts electric. So you can kind of picture these as powering anywhere between kind of 30,000 homes and 300,000 homes, or kind of the rough numbers. And so the advantage of these SMRs, these small modular reactors, is that they can scale in their deployment to meet the demands and kind of enable factory modularity. So they're going to have smaller capital costs. They're just smaller units. You can construct either large portions of the reactor, or maybe even the entire reactor in a factory. And that really enables the manufacturing economies of scale. It's this idea that if you can do something a lot more efficiently in a factory, it could lower the overall cost of the product. And that's one of the proposed advantages of SMRs. The one challenge is as you start to make a reactor and smaller, you lose some of the economy of scale at the facility level. And so you have to, it's a bit of a trade-off between having a reactor that's a little more expensive just in terms of the equipment to make a set amount of electricity, but you're gaining back some sort of economics in the manufacturing process. So it's a trade-off. And then you can see there are some, again, just very interesting advantages associated with the technology. And the last one we'll get to are microreactors. And this is the idea of reactors that are even smaller. So smaller than 30 megawatts electric. It's very, very small reactors that are a fraction of the power output that we currently have today. And the idea is that these reactors could scale for off-grid or remote reactor deployment. They're extremely small reactors, so they can meet small grid needs. Many of the ones that are proposed are fully factory constructible. So you'd actually just have even a sealed reactor that could get sent around, and has much lower inherent hazards. You can imagine that this reactor is 30 to 40 times smaller than existing reactors. So even with the simplest analysis, you can tell that the potential consequences of accidents might be 30 to 40 times lower. So you really are trying to look at just a much smaller, much simpler reactor. The one disadvantage is that you are going to be likely paying a higher price on your capital costs on kind of a $1 per kilowatt hour basis. And so this is something where you might see microreactors deployed to areas where they might currently have a very high price of electricity due to the remote nature, but you probably wouldn't see a microreactor deployed in every single neighborhood in the US. But that being said, depending on how you can look at the economies of scale for your manufacturing, that is a very interesting future opportunity. And so you can see we now kind of have this large spectrum of the power output of reactors that can vary based on the desired application and desired markets. So the last thing I'll just kind of jump into is a few just really quick kind of guess who case studies looking at how the reactor design can enable this deeper characterization. So if we looked at a reactor that was maybe gas cooled, triso fueled, and an SMR, we might be talking about the X Energy XE100 reactor that's currently proposed by X Energy. And so this is a reactor that can provide scalable electricity and process heat, could be factory constructible due to the size of the reactor, has a very established fuel safety characteristics due to the triso fuel and the gas coolant, and could kind of reduce or eliminate offsite requirements. And so hopefully you can kind of see now, after we've talked through the coolant, the fuel, and the power, how these three attributes kind of directly tie to these four characteristics about the plant. It gives you some idea of how this is all related. The next one, if we took a look at a reactor that was sodium cooled, was metal fueled, but was a large reactor, we could be talking about Terrapower's Natrium reactor. That's one of the ARDP winners, and that's currently proposed for construction in Wyoming. And so this leads to a reactor that has integrated heat and storage. It's got very efficient sodium and metal fuel. It's got economies of scale based on its operation because it's a large reactor. It's got very established stability characteristics based on using an established fuel form and an established coolant. And it's got improved fuel usage and waste reduction associated with these fuels and combinations as well. So again, you can see the direct tie between the two columns. The second to last one I'll hit really quick because I know I've gone a little long on time is the idea of looking at a salt-cooled, triso-fueled, small modular reactor. And so in this case, what we're actually talking about is the Kairos Power KPFHR, or fluoride high temperature reactor. And so this is a reactor that would look at having scalable energy and electricity production, economies of scale in manufacturing, because it is ultimately a small reactor. It's got a very, very safe combination and almost kind of maximizing the safety of using a salt that can retain nuclides and the triso fuel that already retains any kind of release of radiation. And this reactor is actually designed with online refueling to increase its reliability. So it would have an uptime and wouldn't have to go down for refueling outages every 18 months like conventional nuclear does. The final one I'll touch on is looking at a heat pipe cooled, metal fueled microreactor. And so this is an interesting one. We're actually talking about the Oklo Aurora powerhouse. And so this is another kind of proposed advanced reactor where it's looking for remote off-grid compatible with fully scalable manufacturing. It's a very small reactor unit that can be completed. Minimal hazards. It has no moving parts because it is that heat pipe cooling. And the hazards may be contained to the building itself just because it is such a small reactor. And so you can see this ends up being one of the pitches for the safety case of this type of reactor. And so I know I've thrown a lot of technical information at you, but I really hope what this is kind of highlighting is that kind of understanding the underlying technology can help you understand what the proposition for advanced reactors are and some of the larger discussions around the technology. The NIA primer goes into a lot more detail on a lot of these, whether it's looking at individual reactor designs or whether it's talking a little more high level about things like the Advanced Reactor Demonstration Project summaries. Also recommend there's a glossary term, so if anything I said sounded like gibberish, I really hope it's going to be pretty well defined in the back of that. So with that, that was a lot of nuclear engineering for about 30 minutes, and so I'd be happy to take your questions and turn back over to Sarah.
Well, thank you so much for a truly wonderful and informative presentation. I really appreciate your ability to take such a complex topic and put it in more readily understood terms. So really, thank you for that. So we'll now be moving into the Q&A portion. So if anybody has a question, please go ahead and click the little raise hand icon and I will be able to see you and make sure that you are acknowledged. But just a question from me to get the ball rolling. How and when can communities get involved with advanced nuclear technologies?
Judy, do you want to take that?
Yeah.
Yeah, go ahead.
So I would say the sooner the better. I think you guys have actually been thought leaders on this. I think there is a little bit of a history around development projects of any kind, not just nuclear, where somebody wants to build a facility, in this case, a power plant, and then they try to convince the community about, why it's a good idea. And our hope, and I think a lot of the developers are thinking along these lines, is to work with the community to figure out what they need and have them involved from the beginning in making sure that the plant is sited and operated and designed in a way that's helpful for that community. So I think becoming proactive on that is a good idea. And also we certainly advocate, and I believe the advanced reactor developers are open to this, for having community engagement right from the beginning.
Great, thank you so much. So now I will kick it over to David Replock and then over to Kara.
All right, my thanks as well. I think that was a great presentation, and me as a political science and history major, I understood just about all of it. So it was very well done, and I appreciate all the information. And as quick background, I'm with TRIDEC. It's the economic development organization in the Tri-City area near where the XC100 reactor will hopefully be built soon. And so we've been pretty closely tracking a lot of the different activities in the advanced reactor world. Had a couple of questions. First one is kind of specific to MMRs. And when you look toward the future, a lot of what we hear about is kind of the evolution of the entire grid, where transmission infrastructure might look a lot different. There's, with all the different environmental impacts of high voltage transmission lines, that those are going to be harder to site new ones for a large new generation source, or the goals of additional distributed energy generation, bringing on more intermittent renewables, and so the need to sort of load follow. And so I guess my question there is, when you look at the potential use cases for a SMR versus a MMR, you're looking out 30, 40, 50 years. I'm just curious if you have any thoughts on how the nuclear technology might be evolving and applied best to those changing scenarios. And I have one more question after that, but I'll stop there for right now.
Yeah, great question. Real quick, by MMR, you're talking about the microreactors? Just make sure I have the right acronym. Okay, perfect. Yeah, no, I think it's a really interesting question about how, and again, it's going to be a little bit of a punt here, because it's going to get into a larger question about how we design our electrical grids of the future. How are we looking at kind of dispatchable assets, whether it's advanced nuclear energy, whether it's fossil fuels with carbon capture and sequestration, or whether it's variable energy sources like wind, solar, or maybe even sources like geothermal. How are these all going to work together to meet the energy demands that we have? One of the unique things about a nuclear power plant, and they often say, is that it's a century asset. You're building a power plant that might operate for anywhere between the next 60 to 100 years. And trying to imagine what the energy system of 2121 is going to look like is not something that I'm willing to put any bets on. So I think when we start looking at different technology choices, how can we come up with reactors that provide the flexibility to integrate into the low carbon grid or the clean energy grid that we're interested in the future, and that don't necessarily represent a kind of a big disruption or a big burden to that. So I think in some cases you might see SMRs as a really good resource in terms of, oh, we know we're going to have established energy demand, or we're expecting to have some industry that we're going to decarbonize. While in other cases, you might say, hey, a microreactor does make sense here because maybe we're not expecting a huge bit of demand growth. So we don't necessarily need that flexibility in how much energy we're producing. We might want to put down smaller units as necessary. I will not pretend to be an expert on how to design an electrical grid, but I know that's going to be a really interesting challenge, is just how to do those predictions and make that resource allocation.
Great. Yeah, thank you. And that's, one of the things that we just have been tracking, especially is, and I think to your point too about how potentially some of this advanced reactor technology can be used for industrial purposes using the heat, and potential roles for microreactors for that. But the other question I had, and I'm just curious, I don't know if you all have really been looking into it yet, but any thoughts on the changing sort of supply chain needs for these advanced reactors, especially when we look at HALEU manufacturing and that sort of thing? I know that the Department of Energy has been looking into that to some degree, but just any thoughts you have on the supply chain of the future for advanced reactors and how that's same or different than kind of what we have for the existing fleet?
Yeah, Judy, do you have any initial thoughts? I'll kick it over to you first.
Sure. So we definitely need HALEU for most of these advanced reactors, not all. And so there is a little bit of a chicken and egg problem with, how do you get the supply chain developed in parallel with developing the reactors, because the people who are going to supply the HALEU want to be sure they're going to have somebody to sell it to, and the people who need the fuel want to make sure they can get that they can get it. So there's a number of ideas now out there. There is a, under the Energy Act of 2020, DOE was required to start thinking about this. There are a bunch of people working on how to jumpstart this system. And we probably need both more policy and investment to make this happen. And we also need very close collaboration with the private sector. So this is going to really be a public and a private effort, because you want ultimately to have a functioning market, but you probably need early government support to help get that market going.
Yeah, I think the only other thing I'd add on that is that I think there's a really interesting opportunity for microreactors and for any, or really SMRs and microreactors, if you're looking at factory constructible reactors, that this is something where it's not just going to be a single plant that's, as they normally say, stick built at a single site, where you're having workers coming in and having 40 or 50,000 workers on site for years at a time. And so I think it might be interesting opportunities for how you're actually building out that longer term supply chain of really focusing more on factory construction than site construction. And that's, I think, just going to depend heavily on just which reactor technologies end up being favorable in the marketplace and how they choose to structure their supply chains. But I think there would be really interesting opportunities there.
Great. All right. So I will just direct your attention. There's a question in the chat. Michael Zimmer asked if anybody had a comment on the role of thorium as a fuel alternative.
I started typing out an answer to that, but Judy, do you want to take the first pass, or can I jump right in on the
go
thorium
ahead.
question? Great. Yeah, so thorium is a really interesting fuel. So for anyone who doesn't know, thorium is 2 squares over on the periodic table from uranium and has a lot of similar properties to uranium. If you take thorium, one of the isotopes, the most common one, thorium-232, and add a neutron, it eventually becomes a uranium isotope that you can use inside of a nuclear reactor and for nuclear reactions. And so there's a lot of interest in thorium because it has a much higher natural occurrence on Earth than uranium. There's orders of magnitudes more thorium on Earth than uranium. So oftentimes when people are talking about powering entire global civilizations on nuclear energy alone, thorium becomes a really attractive opportunity because you need that much fuel. Thorium, however, does have some challenges just related to fuel manufacturing. It can be a lot more difficult to manufacture. There are some safety challenges and just kind of a lot of questions around it. And so I think the really big thing to think about when we talk about thorium as a fuel alternative is, why are we choosing thorium? What is the advantage of that over uranium? And does that make up for some of the additional challenges? Right now, I'd probably say no, it doesn't really make a ton of sense right now, just because we do have ample supplies of uranium. But there are some countries, such as India, that definitely are pursuing thorium as a fuel just because they have large natural supplies of thorium inside their country. So near term, I'd probably say not a lot of thoughts on thorium as a fuel alternative, but that is something that some countries are looking into and might be kind of a much longer term solution, maybe after 2040, 2050. But I'm not going to, again, try to have anyone buying thorium stock based on what I'm saying.
Great, great. So next up, we have a question from Mayor Casper.
Thank you. The report talks a little bit about the levelized cost of energy and how that's a factor. I have found that when utilities are talking about the adoption of a new technology or acquiring, some sort of generation, they are definitely interested in looking at that levelized cost of energy. That to them is the magic number, and it matters a great deal because they'll compare across gas and wind and solar and nuclear, and they'll, or hydro, whatever it is, and they will, zero in on the ones that are cheapest. And many times we find that nuclear, it's cheaper than wind, but it's definitely up there. And so I was very intrigued by the fact that many of your analyses talked about, a significantly lower LCOE. And so I am wondering if you have any plans maybe of going into a little more depth on that somewhere else besides in this primer, simply because that is the fundamental obstacle to adoption for nuclear in many board level conversations that I'm aware of. And in the end, if the utilities don't think it's a value on the dollar, they will choose something else in the short term, even if the environment is at risk, because money seems to matter a lot when it comes to being able to get work done. And citizens might say they're interested in non-carbon emitting sources, but if their bill goes up by 150% or whatever, or to 150% of what it was last month, they're going to be pretty frustrated. And so boards are very sensitive to that. So can you tell me just a little bit more about what your thought is on any of that?
Yeah, I'll just say a little, maybe Patrick wants to chime in. So I'm so glad you asked that, because we are planning to do some more work on cost. The primer is really focused on the technology. How do these things work? Why would you be interested in them? But we are planning to do some work on cost, and would love to talk to you further about what would be most useful. So LCOE is a useful metric, and we all look at it, but it isn't the only important metric. You really want to look at system cost. You have to look at the whole energy system. So it could be that you have power plants that maybe on an individual basis have a higher levelized cost of energy, but they give you a certain amount of reliability that you need to make sure that the whole system works. And we do have some problems in our power markets right now where they may be overly reliant on just looking at the cost of that sort of last hour of energy produced, and not enough on making sure that we maintain a system that can be reliable under any circumstance. Electric reliability is very valuable, a little bit hard to translate into dollars, but it's very reliable. And as our society becomes more and more dependent on electricity, it's even more valuable. So it's very important that we look at the whole system, and you can imagine a system that's a mix of nuclear power and renewables and a whole bunch of other types of power plants, all of which have different characteristics, and then together as a system, they work really well. And so we do have to make sure that we look at system costs and not just LCOE.
Thank you.
All right, so I know that we have a hard stop at 2. We have one further question from Ben Cross about standardization being the key to cost-effective nuclear. Question is, how many different standard reactors are economically feasible? If this is something that somebody wanted to jump in and answer quickly, we can end on that, or I understand that y'all are working to make the slides from today available, so that could be a question for further discussion at some other point, whatever y'all would prefer.
I'll just give the quick answer on that one because I was already typing out and I can just read what I wrote. It's a great question. I think it's hard to say based on the different niches associated with nuclear energy. You can picture how different standard reactors compete in different markets. For example, that little micro reactor that powers 1,000 homes is not going to necessarily compete with a 500 megawatt reactor that's powering industrial process heat. And so I think the better question is kind of what role does nuclear energy play in the future? Where are the different niches that it can fit in? And within that, kind of what is the size of that market? So I think there is kind of a wide open space. We're not just looking for one, but it also depends on kind of what support we provide from a policy level and from a societal level at looking at nuclear as a significant role in decarbonization. So hopefully at least one. I really want there to be at least one standard design, but I think there's potentially a very high number of standard reactors would be feasible.
Great. Well, thank you everyone from NIA for a wonderful presentation and a really great primer. And thank you so much for this discussion today. Thank you to all ECA members who were able to attend today. We will be working to make these slides available to y'all soon. And with that, I hope everybody has a wonderful rest of their day. Take care.
Thanks so much for having us. We look forward to further collaboration.
Thanks, everybody. This has been really, really educational and in English. Have a great day. Thank you so much.
Great.
And if we can
Thanks
be
so
of
much,
help, please
everyone.
let us know. Take care.